Okay, so let's go over some examples on continuity where we might use this, especially problems in the homework. And some of the problems in the homework, you're going to end up with a rational function. So there's a neat theorem about a rational function. So rational functions. So if you remember, rational functions, you have a polynomial in the numerator, polynomial in the denominator, and all rational functions, they are, the big discontinuities that can happen in a rational function is you either have a vertical asymptote, or we had a removable discontinuity. We used to call those holes, but now we call those removable discontinuities. And the reason we had those two things was if we had a pole. So if you remember, if you have something in the denominator that makes it equal to 0, then it was undefined, and we called that a pole. So that's going to be our theorem. And our theorem states every rational function is continuous at every point where its denominator is different from 0. So let's look at an example here. At what points is y equals x plus 3 all over x squared minus 3x minus 10 continuous? Alright, so that's a question mark. That's an S. Alright, so here is our rational function. So we have a polynomial in the numerator, polynomial in the denominator. And polynomials are continuous everywhere. That's, based on how they act. But when you have a polynomial in the denominator, then what happens here is anywhere that this equals 0, you have the possibility of having, well, if this is 0, then you do have a undefined point, and so you do have a discontinuity. Then the question just becomes, is it a removable discontinuity? Is it a infinite discontinuity? Or we'll just say a non-removable discontinuity. I think that's what the homework does. So let's look at an so we have our function y equals x plus 3 all over x squared minus 3x minus 10. So let's go ahead and get our zeros. Remember that we had our zeros. That was x plus 3 equals 0, so x equals a negative 3, easy enough. Then we need our poles. So we have x squared minus 3x minus 10 equals 0. And we got to factor that. So what do we get? We get x minus 5, x plus 2. Yeah, I think that's right. So then we get x equals 5 and x equals a negative 2. So we know at 5 and negative 2, because this is what makes the denominator 0, we know those will be discontinuous points. The question is, are they removable discontinuities or non-removable discontinuities? In this case, they are non-removable because we don't have a matching 0. So if you have a 0 that matches a pole, that became, we called it a hole, but that becomes a removable discontinuity. If you don't have a 0 and a pole matching, then these all became vertical asymptotes, and so therefore they are non-removable discontinuities. So we'll just say y is continuous at all values of x except at x equals 5 and x equals a negative 2. X equals 5 and x equals a negative 2 are both non-removable discontinuities. All right. Okay, so there is an example. One thing I also want to note is that, on the AP test or something, when they say at what points is this continuous, another way to write is using the interval notation. So you could see also, so let's say another way to answer is by saying negative infinity, comma, negative 2, union, negative 2, 5, union, 5, infinity. Okay, so notice how basically we're saying it's continuous at everywhere but negative 2 and 5. So that also works. All right, one more example for this video. For what value of a is f of x equals the absolute value of x plus 3 for x is less than 1 and ax squared for x is greater than or equal to 1, continuous at every x. So that's a question. All right, so here's a good example. We have a piecewise defined function. And let's look at this piecewise defined function. Okay, so the absolute value of x plus 3, we go up 3 and we have this absolute value until we get to there. And notice that it's only for x is less than 1. So from 1 on, from 1 to the negative, it's defined, and then from 1 above, that doesn't count. Now from here though, from 1 on, we have this ax squared. So somewhere down here, we have ax squared. So this would be the absolute value of x plus 3 and ax squared. Now at this point, at this moment, we do not have a continuous function. This is down here. This is up here. All of a sudden we jump down and we come up. However, we haven't decided what a is. So notice that a, we have a way to change how this parabola acts. And so because of that, we can somehow, we should be able to figure out a value of a where this parabola actually doesn't start down here, it starts up here. So the question is, what is the value of a where we can take this, move it, not move it, but make it so the function comes up here and then goes on, and then we have a continuous function. Alright, so let's go through this. First, let's figure out what this value is. And everyone's like, well, it's 4. Well, we do have to be a little bit more, again, rigorous. We have to be very thorough in how we explain this. So using fancy math notation, we're going to just say, well, what's the limit as x approaches 1 from the negative side of f of x? Well, that is going to be the limit as x approaches 1 from the negative side of the absolute value of x plus 3, and we substitute, so we get the absolute value of 1 plus 3, which is 4. So there is a better notation-wise way of showing that that is 4. Now, if this is going to be true, we have to say that if this is going to be continuous, we also have to have the following. The limit as x approaches 1 from the positive side of f of x must also be 4. Because for this to be continuous, the limits have to be equal. So let's go ahead and the limit as x approaches 1 from the positive side of f of x is the same as the limit as x approaches 1 from the positive side of ax squared, which is a times 1 squared, which is just a. So, in order to be continuous, the limit as x approaches 1 from the negative side of f of x must equal the limit as x approaches 1 from the positive side of f of x. Well, from the negative side, this is 4. The positive side is a, and there we have it. So a equals 4. Okay, so there was a lot in this video, but we have the concept of continuity. We have the continuity at a point, which you have to meet these 3 tests. We have the continuity on an open interval. We have a continuity on a closed interval right there. And when it comes to a rational function, it's pretty easy to figure out where it's not continuous. It's because anywhere the denominator is 0, it's not continuous. And then we had this nice problem here where we just kind of looked at, well, what do we have to do with these unknowns that we have to make this continuous?